Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4, and we are on chapter 15, the phosphorus cycle. And right now we're looking at the effect of eutrophication upon phosphorus loading, and we are in this area of that section. The retention capacities for phosphorus can differ considerably between stratified natural lakes, polymictic lakes, and reservoirs. Much of the difference in phosphorus retention focuses on marked differences in water retention times. Water retention time can be estimated by the number of days needed in a given year to fill the lake or reservoir if it were empty. Water retention can be correlated to the phosphorus retention capacity, estimated as a percentage of the total phosphorus loadings remaining and not lost from the water body via the outflow. Although the phosphorus retention capacities are similar, greater than 50% of phosphorus loading for water retention time over a year or longer, the water retention times of lakes are much longer, 1 to 7 years in average, than those of reservoirs, often less than 100 days and highly variable. The differences are most pronounced at water retention times less than 100 days. These differences are related in part to more rapid sedimentation of particulate phosphorus and removal of outflow water deep in the stratified waters in reservoirs versus the slower sedimentation of biotic particles and water removal by surface outflows that predominate in lakes. Figures 15-14, phosphorus retention capacity of lakes and reservoirs as percentage of total phosphorus loadings retained in relation to water retention time. So, x-axis we have the phosphorus retention capacity in percentage of phosphorus loading retained. So that is the amount of phosphorus that the specific water body has retained. And on the x-axis, we have the water retention times in days. So we have the retention of phosphorus capacity and then the water retention times. So for lakes, for example, we can see that that the phosphorus retention is lower in percentage than it is for reservoirs. And the other thing that we can see is that there's somewhat of a linear approach to some degree for the lakes, where reservoirs we have it's kind of bimodal. We have like phosphorus retention like increasing drastically in the first days. I mean, in the first, like, let's say 20 days, so 30 days, and then becoming very stable at 80 in even like decreasing maybe a little bit through time to like 600 plus. So when we think about it as well here, 600 days, that is getting close to 2 years, right? So here we're looking at a phosphorus retention over a very long time. I mean, long time enough. Effects of decreasing phosphorus on other lake characteristics. Changes in ecological structure and physical chemical characteristics can also be expected with reduction in phosphorus concentration. Water clarity will increase as phytoplankton densities decline, and oxygen concentrations in superficial sediments will improve as the supply of new organic matter to sediments declines. While this is most evident in the hypolimnia of thermally stratified lakes, the same holds true for the sediment water boundaries in polymictic lakes. Hypolimnetic, benthic, and cold water fish communities will be less impaired as oxygen levels improve. While phosphorus directly regulates productivity in most lakes, it indirectly regulates cyanobacteria bloom formation via the impact of productivity on sediment redox because blooms are promoted by highly reduced superficial sediments. Therefore, the risk of cyanobacteria blooms decreases as phosphorus loading declines in response to declines in the spatial and temporal extent of highly reduced superficial sediments. In turn, this will lead to the dominance of phytoplankton communities by eukaryotic algae. Collectively, these changes have ramifications for the entire food web. Modeling relationships between nutrient loading and phytoplankton productivity. The cornerstone of eutrophication management since the 1970s has been the control of phosphorus inputs to aquatic systems. Successful restoration of eutrophic systems and preventing systems from becoming eutrophic requires decision as to what constitutes a maximum acceptable phosphorus concentration. This is typically based on maintaining desirable lake characteristics such as non-hypotoxic hypolimnitic waters, preventing cyanobacteria blooms, protecting macrophyte beds, and maintaining phytoplankton densities below levels that would turn a lake green. Maximum acceptable phosphorus concentration can then be used to estimate maximum acceptable phosphorus loads. In contemporary language, loads and concentration above the maximum acceptable criteria are considered unsustainable. Open water chlorophyll A and total phosphorus concentration are often used as indicators of sustainable conditions. The pressing need for decision-making tools to guide eutrophication management effort in the 1970s led to an early emphasis on developing empirical and simplified steady-state models. These models do not explicitly describe all key processes and therefore have fewer data requirements than process-oriented dynamic models, yet they can still be reasonably accurate and therefore useful. Early empirical models predicted chlorophyll A as a function of total phosphorus loading by bypassing the phosphorus concentration chlorophyll A relationship, which was implicit in these models. More complex empirical and steady-state models have been developed, as well as non-steady-state process-oriented dynamic models. When phosphorus is added as short-term pills to unproductive lakes or ponds, either experimentally for purposes of intentional fertilization or in effluents resulting from human activities, the usual response is a very rapid increase in phytoplankton productivity. Increased productivity is not sustained as nutrient loadings are reduced, however, but decreases over rapidly in a few weeks or months to levels near those prior to the addition. Losses in the colloidal fraction and from sedimentation of particulate phosphorus result in continuous reductions of phosphorus from the trophogenic zone. Inputs to the system must be maintained in a continuous or pulsed manner in order to sustain the increased productivity. In other words, steady phosphorus loading of the system is critical to sustaining increased productivity in most lakes to low or medium biological productivity. Conversely, in order to reduce the productivity of a lake that is receiving continuous loadings of nutrients, phytoplankton growth is generally decreased most effectively by reduction of phosphorus input rates to below existing loss rates within the lake. Reduction of total phosphorus loading to the water column from external and internal sources is the objective, since phosphorus is the major nutrient in greatest demand in relation to supply. Since the suppression of internal phosphorus loading requires oxidized sediments, external loading targets should be set at levels that prevent excessive production of organic matter. It has been argued that reductions in nitrogen loading should also be pursued in conjunction with phosphorus reduction to lower productivity and decrease cyanobacteria blooms, especially in systems where responses to phosphorus reductions have not achieved adequate goals. This requires removing enough nitrogen to shift a lake to nitrogen limitation, since it is unlikely that nitrogen removal will lower phytoplankton biomass while it remains phosphorus limited. Although eukaryotic productivity might decrease if enough nitrogen is removed, Mollot et al. Argue that as long as sediments remain anaerobic, nitrogen control will not prevent or mitigate cyanobacteria bloom unless nitrogen fixation is limited by supply of trace metals cofactors such as molybdenum and iron. Indeed, decreasing nitrate loading might exacerbate freshwater blooms by promoting lower sediment redox, which seems to have happened in experimentally fertilized Lake 227. However, nitrogen reductions may decrease cyanotoxin production and might be warranted in some watershed to deal with inorganic nitrogen toxicity and eutrophication of marine coastal waters. It should be noted that only phosphorus reduction achieves all of the major freshwater eutrophication management objectives: lower ecosystem productivity, prevention of cyanobacteria blooms and associated cyanotoxicity, and improve hypolimnetic oxygen levels. Moreover, phosphorus is chemically reactive and therefore technologically easier to remove from water than nitrogen, and does not have major reservoirs in the atmosphere that replenish losses. Modeling nutrient loading and concentration. The nutrient loading concept implies that the relationship exists between the quantity of nutrients entering a water body, the lake's concentration of that nutrient, and the lake's biological response to that nutrient input. The effect of this relationship can be expressed by some quantifiable index of productivity. The effect of this relationship can be expressed by some quantifiable index of productivity or water quality parameter. The loading concept was recognized some time ago as applicable to lake changes in response to phosphorus and nitrogen enrichment. Sawyer suggested that if critical levels of dissolved inorganic nitrogen, 300 micrograms of nitrogen per liter, and phosphorus, 10 micrograms of phosphorus per liter, measured at the time of spring turnover in Wisconsin lakes, were exceeded, nuisance populations of phytoplankton would likely develop during the growing season. Vollwinder first formulated definitive quantitative loading criteria for phosphorus and nitrogen and expected trophic conditions in water bodies. He defined boundaries between oligotrophic and eutrophic lakes by relating nutrients loadings to mean depth, and later refined these relationships. Because phosphorus is commonly the initial limiting nutrient to freshwater phytoplankton, as discussed earlier, and because the many processes of nitrogen cycling complicate accurate measurements of nitrogen loadings to lakes, the loading criteria and models emphasize phosphorus relationships. Attempts to combine phosphorus and nitrogen loading into lake enrichment models have also been empirically successful. The concentration loading relationship are all based on the mass balance equation of a substance M between its source and losses in an open system. So we have delta M over delta T is equal to I minus O minus S minus R in parentheses. So delta M is the storage gain or loss of nutrient M over time. Delta T is the time. I is the external nutrient load, so that's the input. O is nutrient loss, that's the output. S is nutrient loss to sediment, so this is sediment. And then nutrient, and R is nutrient regeneration from sediment. So we have some loss into the sediment, but then we have also some regeneration from the sediment. So this is so the input minus the output minus the difference between what the sediment takes compared to what it loses is our change in the storage. While I and O can often be measured directly with accuracy, S minus R is more difficult to measure and is often obtained by difference. Under steady state condition, delta M divided by delta T is equal to 0. Although in reality, steady state doesn't exist in a lake that oscillates, or lakes in the lakes, I'm not sure about that oscillate around relatively constant nutrient loads over periods of several years, exhibit a set of trophic characteristics and may be viewed as a tendency toward a steady state. So that's a little of an unclear sentence, but pretty much what they are saying here is that steady state doesn't exist in the sense that there are so many like dynamic inputs and outputs at any given time that it's difficult to have a steady state where we have like a zero, like a value of 0 between the inputs and the outputs of phosphorus or nitrogen, whichever nutrient we're looking at. Often this steady state is defined as a mean nutrient storage content as measured as spring turnover or as the annual storage content over several years. The model based on mass balance further assumed that the nutrient load is instantaneously and completely mixed throughout the lake water, an assumption that is only partially true for most lakes. The models, consequently, are particularly applicable to a large population of lakes rather than to describing the specific behavior of an individual lake. The predictive ability of these simplistic steady-state models is quite good for small lakes. A simple mass balance equation for predicting lake concentration that takes into account volumetric loading of phosphorus as well as losses by flushing and sediment is given by d over p over by lambda by dt is equal to 1 over rho w by pi minus 1 over rho p by p lambda. So p lambda is the average total concentration for phosphorus, dissolved and particulate phosphorus, so that's dp lambda. Pi, which we have right here, is the average inflow concentration of total phosphorus. Then we have tau, actually it's not rho, tau p, which is the average residence time of phosphorus. So this is the average residence time of phosphorus. And then tau w is the average residence time of water. So therefore here what we're doing is we are multiplicating we are doing the inverse of our residence time of water, so how long the water is in the lake, and we're multiplicating that by the average inflow of total phosphorus. So what we're getting in is by the inverse of the residence time of water, and then we are subtracting a value that is the inverse of the residence time of phosphorus by the average total phosphorus, p lambda. And so that is the difference. So this is an instantaneous, this is a derivative, so this is close to an instantaneous value, in which the right-hand terms represent the average rate of supply to and the average rate of loss of total phosphorus from the lake, respectively, and the left hand represent the corresponding temporal variations of the average lake concentration. Then, assuming steady state and simplifying equation 15.3, we come up with this, which is tau p divided by tau w is equal to 1 over 1 plus square root of tau w. So the ratio of the average residence time of phosphorus over the residence time of water is equal of the inverse of 1 plus the square root of the average residence time of water. An approximate retention coefficient as a function of hydraulic load Q was found to be R is equal to 0.426 E to the power of minus 0.27 Q plus 0.574 E of minus 0.0949 Q, where Q is the aerial water load, hydraulic load to the lake in meters per year, calculated as the lake outflow volume divided by the lake surface area. These two retention values, while not identical, yield similar results for lakes of mean depth between 10 and 30 meters and hydraulic load between 3 and 90 meters per year. When either of these models was used and data plotted to show the extent of prediction of spring turnover phosphorus concentration from loading, they describe the average statistical behavior of lakes in terms of the relationship between phosphorus load and phosphorus accumulation within the lake. Deviant lakes could be shown to have mechanisms operating to overestimate or underestimate the loading. The steady-state relationship between phosphorus loading and concentration can also be expressed as Dillon and Riddler, and so then they have Tp is equal to load divided by Q plus V, where load is the total of total phosphorus from all external and internal sources in milligram per meter square per year. Tp is the mean annual whole lake total phosphorus concentration in milligrams per meter cube, equivalent to the commonly used micrograms per liter. Q is the water discharge rate in meters per year, And V is the generalized loss coefficient representing settling loss of phosphorus to the sediment in meter per year, because there is no gas phase and thus no loss to the atmosphere. In this formulation, the fraction of the load retained by the lake is given by R is equal to V over Q plus V. This version of the mass balance relationship forms the foundation of the lakeshore capacity model, which was developed to predict the impact of shoreline development on water quality in forested areas of central Ontario. These authors viewed multi-year runoff loading and concentration means to be an approximation of steady state with differences between model predictions and observation for a given year often being large compared to differences between predictions and multi-year means. Empirical models should be calibrated with high-quality regional data for predicting relationships within that region, but when data are not available, models from other regions or models calibrated with combined data set from different studies could be used with the understanding that lake responses may deviate substantially from model predictions. And that will be it for today, and tomorrow we'll pick it up with modeling biological responses to nutrient loading. Thank you for chiming in today, and I'll see you tomorrow. Have a good day. Bye.